Case study: successes and challenges of the validation content reuse. Abstraction. At Intel, the AI validation team created an internal test content used to validate the full functionality of the various IPs in the SoC. This content is flexibly designed to support different pre-silicon and post-silicon environments and has been used to validate the successive generation of IP revisions. This content is also scalable, has been reused in SoC validation while these IPs are ultimately integrated. This paper discusses the challenges to apply the reuse from the IP to SoC and the key design and strategic design that we made to overcome them. We discuss our results, including headcount savings, artifacts found, and operational cost savings. Introduction. Moving the edge is the primary challenge in the hardware today. Variation in the SoC design grow each day as novel uses are innovated. New customers are found and generational improvements are made to industry standard. As much as the challenge exists in the design side of the equation, validation faces the same problem in ways that grows exponentially in complexity. As our portfolio expands to include new IPs, the new IPs on the evolving IPs and the emergent features which cross IP boundaries, the responsibility of the validation teams to verify the functional correctness for all the permutations, combinations of how different the agents on the platform interacted is an MP complete problem. Adding the complexity of the IP versus SoC validation, pre-silicon versus post-silicon validation, and differences in the execution, the platform configuration, real devices, virtual devices, platform capabilities. One result is a complex problem with multiple moving parts. Designing software to validate for this ecosystem is an equally difficult problem to solve. How do we find efficiency in such an ecosystem? What approaches can take to simplify the problem space into smaller, tractable problems that we have to hope to finding solutions for? What challenges have we faced to continue to face in this domain? We have taken a multi-year journey down the path to the create validation content to validate IP in pre-silicon validation, extend this SoC validation, and ultimately use this manufacturing. In this paper, we will discuss how we have tackled the growing challenges through the reuse, our approach to solving scalability problems, and the result of this effect. 2. Grocery terms. The terms definition: API application programming interface. Bare metal is a minimal validation environment without operating systems. FPGA is a field programmable gate array. HAR, the hardware abstraction layer, just-in-time input-output. Intellectual property refers to the discrete functional blocks implementing a specific protocol or the function within an SoC. ISA instruction set architecture, original equipment manufacturer, OEM. Post-silicon phase of the project occurring on physical prototype units. Pre-silicon phase of a project development prior to the ability of the silicon prototype unit. PSS is a portable test and stimulus standard. Register transfer language, object code for specifying the designing circuits and systems. Communication paths other than the primary objective subbus. System on chip. Manufactured version of the SoC. More software functional model of the bus or endpoint. Test time reduction. Background. IPs serves as a foundational building blocks for the SoC design. At Intel, we deal with many different domains of the IPs: high-speed IOs and low-speed IOs, security, context, audio, storage, and etc. Thorough the validation of these IPs is crucial to ensure the proper function of the IP in the varying and unanticipated ways. The goal for our validation is to validate the specification. Any behavior that is compliant to the specification must be supported. This includes different perturbations, combinations of settings for an operation. This also includes different behavior of the IP, both sequential and parallel. The end goal is to validate for completeness of the spec and also to subject the IP to highly stressful workload to ensure the proper functionality. All of this allows us to thoroughly assess microarchitecture, design, internal state, and any shared resources. IP validation is executed on two platforms, IP emulation and FPGA. FPGA platforms allow the IP validation to the test IP with the real devices and test card. On emulation platform, endpoint device differ. In some cases, virtual versions of the test card may be used for validation. In most cases, transactions are used to emulate the traffic between the controller and IP. Each platform achieved its specification goal toward the validation of the IP, so portability across the platforms is an important consideration for our content. As a result, these differences in endpoint between the platforms created challenges to implement extensible validation content. SoC and subsystems are treated as a collection of the IPs with additional integrated logic. The focus of validation is to ensure the correctness in the integrated of IPs, cross-IP flows and interactions, subsystem SoC flows and digital analog layer integration. There is less emphasis on the depth of the IP, but a focus on the role of the IP within the broader SoC or subsystem operation. Executing system flows often place a requirement upon the IP, which IP content must scale to support. IP content is also needed to validate normal operation after system flows. Running IP operations successfully ensure the IP readiness. Thus, IP operations are used to a means to validate integrated into the SoC. SoC validation is executed in emulation and post-silicon platforms. Similar challenges of the IP validation platforms exist here. Emulation uses transactor and limited usage of the virtual devices, while post-silicon platforms use real devices and test card. Additionally, change in the platform support exists between the IP and the SoC platforms. Power management and sideband across the access to fuse support are a few of the differences between IP and SoC platforms. SoC platforms are also configurable as product SUKs are needed to be configured and tested. All of these variations add additional challenges to our ability to scale content. Parts screening in the manufacturing also present its own challenges. Limited post-silicon platforms and the constraint of the manufacturing environment also place constraint on the type of post-silicon platforms and the devices that are used. Additionally, not only are the types of the device different, but due to the need for the thorough screening, more units are needed to thoroughly screen all the I/O interfaces. The challenge that we face in validation content development is multifaceted. How do we address the depth of the validation needed for IP validation? How does this content scale to the SoC validation and ultimately to the screen or the interfaces in manufacturing? How easily can the content design scale to the integrated and support to new SoC content? When we examine the different challenges of executing across the wide diversity of the platforms, how does the content scale to detect and support different endpoint devices? Chapter 4 is solution. Our software architecture centers around a simplified software stack and the proper adherence to roles and responsibility in each layers of the stack. As shown in Figure 1, the software stack consists of 4 main blocks of the code. Our primary motivation in the software stack architecture is to design with reuse in mind. This reuse not only includes reuse in validation, but also allows for evaluation in how the code can be used. It's convincible that our code must be used in the bare metal kernel driver code for various operating systems like Windows and Linux, or even as a user code in an application. Figure 1. IP validation software stack. The hardware abstraction serves the main layer for the code Portability, providing APIs and services for operating systems, hardware access. Access to operating system services like logging and thread control and memory allocation are restricted. Hardware access to the devices over memory after I/O also have AI functions. All of our code is built on top of this layer. Figure 2 is sample hardware OS abstraction functions. The data generation layer serves as our code block that allows us to set up parameters in the IP and any data buffers that are needed. This code does not touch the hardware. No controller programming is implemented in this layer. Rather, any choice that needed to be made for the API IP are resolved in this layer. Users have the ability to specify the different values for the computation nodes, which are resolved in this code are operational parameters used whereas in the code. Data buffers are allocated populated with pattern data for IP operations. Code this page consolidated all design makings so execution on the target can be efficient as possible. As a result, this code can be shifted left to the execute. Earlier, the test build execution flow executed as part of a JIT or the target setup code. Figure 3 is sample data generation code. In the data generation, we utilize the structure as our primary mechanism for data transfer. With the integration into a modeling front end, we try to keep the interface's functions as static as possible in order to minimize the change in the code. By utilizing structure, we found that we can keep the interface static as new validation nodes need to be added. We can simply modify the structure and implementation that support that structure without having to modify the interfaces and modeling. The device library layer is what we refer to as our business logic layer, where all the IP programming sequences reside. Code in this layer accesses the control and encompasses code to initialize and configurations IP, program operations, or even programmatic sequences for handling interrupt. Inputs are taken from the data generation layers, so we minimize the amount of the non-IP code being coded alone during the execution phase. The other restriction placed on code in this layer is that the OS services are not used. This code is intended to be portable across the multiple targets, so we keep it as diagnostic to the OS as possible. Figure 4 is the same device library. The drivers comprise the final layer in our software stack. Drivers serve as a mechanism to measure to the user intent during the execution with what is allowed by framework or operation system. Input from the data generations are passed to drivers instances, and any hardware accessed by the driver are accomplished through the function calls into device library. Portability is our main concern with our software stack. The data generation and device library layers are designed for portability so that only need to be implemented once and can be ported to any validation framework without modification. As the foundation for data generation and device programming, the hard layer must be implemented for any new framework to be used. We try to keep the subset of the functions to fully implement the hard as well as possible to minimize work. Drivers are designed and are portable across the framework since they interface directly with their target framework. We assume reuse of this layer is not possible because different operating systems and the validation framework has different implementation to support features like interrupt. However, based on the work done to apply reuse, we estimated this layer to only comprise of roughly 10 to 15% of the overall code. This software stack allowed for the fundamentally needed to access hardware and program One of the problems when attempting to develop the validation contains the fundamental code support for hardware that all applications need to use. With this layer, we believe we've taken a significant step forward to reduce, in many cases, eliminate the hardware support, so we can focus on the validation applications that will help us stress to hardware. Validation applications can reflect different validation methodologies and focus areas. Some applications may focus on the memory controller and caching, while others may focus on the concurrency of IOs or even power management. One approach to an application layer for hardware validation is to utilize modeling. Our current modeling utilizes cadence perspec and SNL syntax, a modeling syntax that predates and heavily influences portable stimulus, to form models of each IP with an eventual full move to portable stimulus. The design of each IP model focuses on defining units of operation at the same level of the granularity as validation test plan. These operations are referred to as content capability and can be combined to create executable tests that are expressed at the operational IP level. The choice in the level of granularity is crucial in effective model design. To high level of flow will result in a similar operation overlapping. Too low level of modeling can devolve into a specific individually registered programming. A key barometer in the judging the correctness of our flows is to examine the modeling action against their realized implementation, where formed action generally share little code for with other actions in the model for programming the intent of operation. These IP models contain all the code needed to be executed the IP using our software stack as a realization layer to direct data generation and drive course at the appropriate time. Applied to the subsystem and an SoC, our modeling treated each IP as an individual subcomponent of the SoC. This allows IP models and their realization layer to exist without the need for any modification. Additional modeling is needed to support cross IP and system flows. These reside as part of the SoC model in order to maintain a clean separation of responsibility between the IP integrated IP model and the SoC. Utilizing this approach, we are able to fully support the functionality of the SoC down to the individual IPs and their operations while only adding the incremental implement and avoiding the rework. Outside enabling the validation of application, we must solve the problems of supporting different platform capabilities. As described previously, platform differences between the pre-silicon and post-silicon and variation the configuration of the platforms create a wide diversity of challenges for validation content to execute on. Misconfiguring our content resulting in mis-execution and wasted cycles. We utilize the strategy to discover as much information as is needed to properly configure and constrain our IP and SoC models. Discovery looks at the capability of the IPs to determine the version and hardware features. It also examines the attached devices to try to determine what types of device is attached to. Along with the information retrieved through the BIOS settings, this gives a full picture of all necessary inputs for our content to run on a platform. All of this information is fed into our modeling, which allows us to enable and disable features based on the capability on the platform, and subsequently generate content that can run on the platform. This process of the platform discovery is critical in our ability to scale across IP and SoC and manufacturing. So the discovery and configuration process allows us to undetected devices and properly support them in their usage model. Result 5 result. Test 5 result. Effectiveness of our validation content is primarily measured in terms of the RTL bugs found. Figure 5 illustrated the number of the RTL bugs found across all IP families covered by the content. The number of bugs is significant as each RTL bug is found in the pre-silicon, which prevents bugs from escaping into real silicon. IP design that is reused across the multiple programs also benefit. Bugs found in the fixed in the pre-silicon result in the cleaner silicon, which helps to reduce additional stepping at the cost of millions of stepping. Figure 5 is the reusable IP content has been successfully applied to across the breadth of IP domain to find RTL bugs. At the IP level, we have the reused content project for multiple generations. As illustrated by Figure 6, reused IP content is effective in finding bugs project over project, with a growing number of bugs found as content as validation continues to mature. Figure 6 is reused applied to the multi-project continue to find bugs, increase effectiveness. Material Lake is currently in flight. The associated bugs found in another key measure of the success of reuse. By reusing IP content and only investing in associated specific flows, associated bugs found are deemed very high in ROI due to the effort expended. Through 4 successive projects, we have found a total almost 200 associated bugs. Figure 7 shows the percentage of bugs found through the content reuse and illustrated the increasing effectiveness of the reuse as the trend finds a higher percentage of bugs green compared to the all bugs found blue. Figure 7 is content reuse applied to associates shows a high effectiveness and found bugs at integration. Our reuse engagement with manufacturing is a key driver toward the operational cost saving. Content is reused in the part screening at the full system level is the last step between finding manufacturing defect and releasing to OEM partners. Operational cost saving through the content reuse is derived from the effectiveness of the screening content, test time reduction TTR, and the resulting throughout the part testing. Sufficient through the based on the test time reduction lower the need for a more screening system to offset test time. The table 1 is manufacturing cost saving from content reuse. The reuse effort to manufacture reduces the total number of the development needed to achieve the same amount of the content. Our development team is roughly 15 is able to leverage our reuse architecture to scale across the broad range of the validation of scope. Areas where content developed would need to be duplicated are naturally across areas where development cost can be reduced. Table 2 shows our estimated headcount reduction over the lifespan of our effort for more project generations by embracing the content reuse. This headcount can be used to provide additional benefit areas in the validation ecosystem. Table 2 is developed headcount saving from the applying reuse. Reuse has also resulted in increased stability of the content. Figure 8 illustrates the number of issues related to content filed project over project, referred as a noise, which strives to reduce noise for every successive project. As illustrated, we found the new content as noisy, primarily due to the enabling, while the bulk of the content base remains stable. Figure 8, content stability drives the efficiency validation execution velocity. Decreasing trend in content noise yield higher quality content. The sixth future work challenges. We face a multifaceted roadmap forward to address the growth of the application of content reuse. Technically implement at the forefront of the continuing proliferating our success. In this area, we are focusing on the three key areas to expand the effectiveness of reuse. Portable stimulus standard. Moving our modeling to fully embracing the portable stimulus industry standard is one of our key efforts. Embracing this standard allows validation to talk at the level of the test plan and create content that reflects this. As an abstracted front-end interface, this gives us the capability to easier adapt our content when the underlying IP and SOC changes. Preliminary scoping showed the application of the standard to the up to 70% of the modeling models. Effort to collaborating with the industry at large is needed to address the identified modeling problems. A related challenge to module portable stimulus modeling is proper encapsulation and support for across IP flows. As advancement in hardware design continue, in the creation of the subsystem of the multiple and integrating interconnected IP is a new norm. We must be able to scale IP modules to support subsystem modeling and interconnected operation and their inclusion in multiple subsystems concurrently, while also supporting standalone IP operations. Third-party interoperability. As the scope of the variety of project grows into future, we see potential for third parties to be integrated with our product. With the IP RTL comes with the need for a validation collateral that is necessary to validate the integration of the IP with the SOC, requiring vendors to support the breadth of the validation platform and operating system frameworks being used is an unreasonable requirement to a vendor. Rather, we look for explore standardized abstraction layers so that driver collateral can be developed on. One of the challenges as Intel expands its foundry portfolio is its ability to scale the validation environment from one instruction set architecture to another. In this effort toward more ubiquitous computing, it's not guaranteed that the old architecture follows the x86. This provides a substantial challenge to overcome, which otherwise will limit the extensive of the hourly use. We continue to investigate solutions that allows us to be portable across multiple ISAs without customizing our content. Portable stimulus serves to standardize the operators of validation testing intended across the industry. As we look at our end-to-end challenges in content space, we feel the end-to-end standardization also provides tremendous potential for efficiency and interoperability. As a standard that materializes as a common verification framework or operating system could lead to a hardware abstraction layer for device programming and as a platform ISA. In a world of increasing SOC complexity of third-party RTL integration, we feel like PSS is the tip of the iceberg. Driving additional standardization further down the realization layers will help increase velocity and quality in the industry. The desire to embrace our content reuse also drives more diverse usage models. Headless execution platforms and environment without a main processor provide one such usage model, both in the split silicon validation as well as in areas such as manufacturing screening. Co-validation of the production software stack with synthetic content presents another opportunity. Mixing production and semantic allow validation to test cutting-edge features in an environment where no device supposed to exist. This capability also allows the pathway into more efficient debug and issue reproduction. We continue we continue to explore reuse down these paths and others to drive validation and debug efficiency, feature coverage, and cost savings. Section 7 Conclusion. Through the multiple generations of our major Intel client project, we have successfully used and reused validation content from IP validation across the generation and into SoC. Validation content was designed and for portability and exercise across the FPGA, emulation, and post-silicon platforms. Each platform is being used to different configuration and capabilities. Starting from our research engagement, validation teams found in the excess of the 600 RTL bugs across the IP SoC. Proliferating the reuse out to the validation, specifically into defect screening, we are able to provide additional benefits into area of reduced operational cost and higher product quality. We continue to drive enhancement in engagement to expand the footprint of reusable content, improve the effectiveness and efficiency when embracing our work. Future work toward fully embracing PSS, varying depth of the coverage target to continue to drive toward higher levels of quality. Additional engagement that leverage our content base continue to challenging, expand our definition, applicability of reuse. All of these efforts will continue to feed a stream of innovative ideas and solutions to benefit Intel and the broader industry. Acknowledgement. Okay, we would like to thank the Intel Vice, VIC software team and management for their effort to reuse IP content. We would like to thank the CAVE software team and the management for their support and effort in adapting synthetic validation content into their methodology. We appreciate our continued partnership with our validation and manufacturing teams as they continue to embrace reusable content into their methodologies. A special thanks to Ernie Jennifer for his sponsorship for this initiative, mentorship, and influence. Today, I'll add this paper, Case Study Successes and Challenges of Validation Content Reuse, DVCON2023. Thank you for your time and see you next time.